Imagine a universe where the boundaries of time are not fixed, where past, present, and future are threads in a vast cosmic tapestry, waiting to be unraveled. Time, as we experience it, seems straightforward, seconds ticking, days passing, moments flowing like water. Yet beneath this apparent simplicity lies a world of profound complexity, one that challenges our deepest intuitions. At the intersection of physics, quantum mechanics, and cosmology, scientists have begun to ask a question that has long fueled both imagination and science fiction: can we truly travel through time? The notion of time travel is not new. For centuries, philosophers, writers, and dreamers have speculated about the possibility of moving through time as freely as we move through space. H.G. Wells's The Time Machine, written in the late 19th century, captivated readers with a vision of humanity hurtling through the ages. But what was once pure imagination is now being explored with the rigor of science. Quantum physics, a field that has transformed our understanding of reality itself, provides a framework in which the seemingly impossible begins to seem, at least theoretically, plausible. At the heart of this exploration lies a key concept: the nature of time itself. Classical physics, shaped by Newton's laws, treats time as an absolute linear progression. It flows uniformly, independent of observers or events. But the 20th century brought revolutionary changes. Albert Einstein, in his theory of relativity, revealed that time is not an independent, universal river. It is intertwined with space itself. Space and time form a dynamic continuum, malleable under the influence of gravity and motion. Massive objects warp the fabric of space-time, causing time to slow down or speed up relative to different observers. This is not science fiction, it is a measurable phenomenon. Astronauts aboard the International Space Station age slightly less than their counterparts on Earth, a subtle but real effect of time dilation predicted by Einstein's equations. If relativity bends time in response to gravity and motion, could it also allow us to manipulate time more dramatically? The idea of traveling into the future is, surprisingly, well within the bounds of physics. By moving close to the speed of light or venturing near extremely massive objects, humans could experience time at a different rate than those on Earth. This is known as time dilation, and it has been confirmed in countless experiments with atomic clocks on airplanes, satellites, and high-speed jets. In essence, someone traveling at relativistic speeds could, in theory, arrive years in the future while only experiencing a fraction of that time themselves. Traveling into the past, however, presents far more profound challenges. This is where quantum mechanics, the study of the universe at its smallest scales, becomes essential. Quantum physics defies our classical intuitions. Particles exist in superpositions, being in multiple states simultaneously until measured. Waves collapse into particles, and entangled particles communicate correlations instantaneously across vast distances. At this microscopic level, reality itself is probabilistic, fluid, and in many ways stranger than any fiction. One of the most intriguing aspects of quantum mechanics is the phenomenon known as quantum tunneling. In classical physics, a particle cannot pass through an energy barrier higher than its own energy. Yet in the quantum world, particles can tunnel through barriers, appearing in locations once thought inaccessible. If the universe allows particles to bypass what seem to be absolute limits, could there exist mechanisms, hidden in the fabric of spacetime, that permit backward travel in time? Physicists have explored this question through theoretical constructs called closed time-like curves. These are paths through spacetime that loop back on themselves, theoretically allowing an object to return to its own past. Such curves emerge naturally in certain solutions to Einstein's field equations, particularly around hypothetical objects known as wormholes. Wormholes, sometimes called Einstein-Rosen bridges, are shortcuts connecting distant points in space and, potentially, time. Imagine a tunnel whose entrance is in one era and the exit is decades earlier. In theory, if one could stabilize such a structure, time travel might be possible. Yet these ideas are far from simple. The universe imposes constraints that challenge our imagination. Wormholes, for instance, require forms of exotic matter with negative energy density to remain open. Such matter has been observed only in tiny quantum effects, like the Casimir effect, and scaling it to macroscopic levels remains a monumental challenge. Moreover, time travel raises paradoxes that threaten the consistency of reality itself. The classic grandfather paradox asks, what happens if you travel back in time and prevent your own existence? Would the universe unravel, or would some yet undiscovered principle enforce consistency? Some physicists propose that quantum mechanics itself might provide an answer. The many worlds interpretation, for example, suggests that every quantum event spawns a branching universe. Traveling to the past might not alter our original timeline, it might simply create or enter an alternate branch of reality, preserving consistency while allowing seemingly paradoxical actions. This concept, while mind-bending, aligns with quantum theory and the probabilistic nature of the universe. Experimental science has even begun to probe the edges of time manipulation. In laboratories, researchers have observed phenomena that resemble time loops on a quantum scale. Photons have been made to interact with their past states, and particles have demonstrated correlations that defy classical causality. These experiments are small, fragile glimpses into a universe where the arrow of time is not absolute, where cause and effect can intertwine in subtle and surprising ways. As we explore these ideas, it is essential to recognize the limits of current knowledge. Time travel, particularly to the past, remains speculative, constrained by the laws of physics as we understand them. Yet the pursuit is far from futile. Every theoretical insight, every quantum experiment expands the boundaries of what is conceivable. In probing the possibilities of time, we confront not only the nature of the cosmos, but the very essence of reality itself. In the coming sections, we will journey deeper into the strange and captivating world of quantum mechanics, wormholes and relativity, exploring how modern physics conceives of time travel, what experiments hint at its feasibility, and the paradoxes that challenge our understanding. We will examine the mathematics, the thought experiments, and the visionary ideas that have propelled physicists to imagine not just traveling through space, but through time itself. Time, as it turns out, may be far more flexible than our everyday experiences suggest. It may bend, fold, and loop in ways that challenge the limits of imagination. And in seeking to understand it, we glimpse the profound and beautiful mysteries that the universe has hidden, waiting for minds daring enough to explore them. To understand the possibility of time travel, we must first delve deeper into the world of quantum mechanics, the science that governs the behavior of the universe on its smallest scales. Quantum physics is, in many ways, a world apart from classical intuition. Particles are not simply tiny balls, they are clouds of probability, existing in multiple states at once until observed. Electrons can spin in opposite directions simultaneously. Photons can take every path available, and particles separated by vast distances can influence one another instantaneously through a phenomenon known as quantum entanglement. This is a universe that refuses to follow the rules we consider normal. Entanglement, in particular, is striking in its implications. Albert Einstein famously called it spooky action at a distance, because two entangled particles appear to communicate faster than light, regardless of the distance separating them. While entanglement cannot directly transmit information faster than light, it suggests a deep underlying connection in the fabric of reality. Some theorists have speculated that such connections could, in principle, allow information to traverse time, or at least to exist in ways that challenge our conventional notions of past, present, and future. One of the most compelling frameworks for imagining time travel comes from the concept of closed time-like curves, or CTCs. In simple terms, a CTC is a path through spacetime that loops back onto itself, allowing an object to return to an earlier moment in its own history. This idea emerges naturally from solutions to Einstein's field equations in general relativity. Among the most famous solutions is the concept of a wormhole, a tunnel connecting two separate points in spacetime. If one mouth of a wormhole is accelerated to near light speed and then returned to its original position, time dilation could cause it to exist at a different point in time relative to the other mouth. Step through the tunnel, and you could, theoretically, emerge decades earlier. But the universe is a careful guardian of its own consistency. Maintaining such a wormhole is no trivial task. It requires exotic matter, a hypothetical substance with negative energy density. Ordinary matter curves spacetime positively, exotic matter curves it in the opposite direction, preventing the wormhole from collapsing. While we have observed tiny effects reminiscent of negative energy, such as the Casimir effect between closely spaced metal plates, creating a stable macroscopic wormhole remains a colossal challenge, far beyond current technology. Even if such a structure could exist, the act of traveling through time introduces paradoxes that are as fascinating as they are perplexing. Consider the grandfather paradox. If you were to travel back in time and prevent your grandparents from meeting, how could you exist to perform that action in the first place? Such paradoxes are more than philosophical puzzles. They expose the tensions between our intuitive understanding of causality and the laws of physics. Interestingly, quantum mechanics might offer a resolution. The many worlds interpretation posits that every quantum event spawns multiple parallel realities. In this framework, traveling to the past would not alter your original timeline. Instead, it would create or enter a branching reality, allowing actions that appear paradoxical without violating the consistency of the universe. In other words, you could prevent your grandparents from meeting, but this would unfold in a parallel universe, leaving your original timeline untouched. It is a mind-bending concept, but one that aligns with the probabilistic and branching nature of quantum reality. Experimental physics has begun to test some of these boundaries, albeit on tiny scales. In laboratory experiments, photons have been made to interact with their past states in controlled ways. Certain setups allow information to propagate in patterns that mimic temporal loops. Particles can seemingly anticipate future events, displaying correlations that defy classical cause and effect logic. While these experiments do not allow us to jump decades into the past, they provide tantalizing glimpses of a universe where time may be far more flexible than our everyday experiences suggest. Another crucial concept in this discussion is quantum superposition. In the quantum world, particles can exist in multiple states at once. A particle can be in two locations simultaneously, or spin in opposite directions at the same time. Only when measured does it collapse into a definite state. This fluidity of existence challenges the classical idea that the past is fixed and immutable. If fundamental particles themselves operate outside of fixed temporal order, could larger structures, at least theoretically, be influenced to navigate time in ways that seem impossible in our macroscopic world? While these ideas are largely theoretical, they are grounded in real mathematics and physics. Solutions to Einstein's equations, combined with the probabilistic nature of quantum mechanics, suggest that the universe does not forbid backward time travel outright. It merely makes it extraordinarily difficult. Time, like space, is not a rigid, immutable dimension. It can stretch, warp, and fold under extreme conditions. Yet the requirements for such manipulation, exotic matter, precise control of space-time, and the avoidance of paradoxes, are so demanding that they place practical time travel firmly in the realm of speculation, at least for now. Despite these challenges, the pursuit of understanding continues. Theoretical physicists construct elaborate thought experiments, imagining particles, photons, and even humans navigating temporal loops. They calculate the effects of massive gravitational fields, near light-speed travel, and quantum entanglement, seeking consistent solutions that respect the laws of physics. Each equation, each model, brings us a step closer to understanding not only the possibility of time travel, but the fundamental nature of reality itself. In exploring these ideas, we begin to confront profound philosophical questions. Is the past immutable, or is it as fluid and probabilistic as the quantum world suggests? Could the universe accommodate multiple timelines, each branching from the choices and events of the present? And if time travel were possible, what responsibilities would accompany the ability to influence events across eras? Our journey into the quantum mechanics of time is only beginning. In the next section, we will examine the theoretical physics behind wormholes in more detail, exploring how general relativity and exotic matter could, in principle, create shortcuts through space-time. We will also look at the experiments and hypotheses that hint at the edges of temporal manipulation, drawing connections between theory, observation, and the enduring human fascination with moving through time. Time, it seems, is not a simple river flowing in one direction. It is a complex, dynamic dimension, intertwined with space, quantum phenomena, and the very fabric of reality. Understanding it requires not just mathematics and physics, but imagination and curiosity, a willingness to question the assumptions that define our experience of existence. To explore the possibility of time travel more concretely, we must turn to one of the most extraordinary concepts in theoretical physics, the wormhole. Imagine spacetime as a vast, flexible fabric. Normally, the shortest path between 2 points is a straight line. But what if this fabric could fold, creating a tunnel that connects 2 distant points, not only across space, but potentially across time? These hypothetical tunnels are called wormholes, or Einstein-Rosen bridges, named after the 2 physicists who first described them mathematically in 1935. A wormhole is a solution to Einstein's general relativity equations, which describe how mass and energy warp spacetime. While most solutions describe familiar phenomena, planets orbiting stars, light bending around galaxies, some describe far stranger structures. A wormhole is one such structure, a tunnel connecting 2 regions of spacetime. Step into one end, and in theory, you could emerge light years away in an instant. Step into a specially configured wormhole, and you could emerge decades in the past. The concept of time travel through wormholes is closely linked to time dilation, a relativistic effect predicted by Einstein. If one mouth of a wormhole experiences significant acceleration or is placed near a massive gravitational field while the other remains in a more typical environment, the flow of time at each mouth differs. This means that while only a few years may pass for one end of the wormhole, decades or even centuries could pass for the other. If you enter the slower mouth, you could emerge in the past relative to the other mouth, effectively traveling backward in time. But creating or maintaining a wormhole is far from trivial. According to general relativity, a natural wormhole would collapse instantly, preventing anything from traversing it. To stabilize it, physicists theorize the need for exotic matter, matter with negative energy density that counteracts gravitational collapse. Unlike ordinary matter, which pulls spacetime inward, exotic matter pushes outward, holding the wormhole open. While we have observed tiny effects resembling negative energy in quantum experiments, such as the Casimir effect, scaling these effects to a macroscopic level remains purely theoretical. No practical method currently exists to generate or control exotic matter in quantities sufficient to stabilize a wormhole. Despite these challenges, wormholes offer a tantalizing glimpse into the possibility of bending not just space, but time itself. The mathematics of general relativity provides consistent solutions where closed, time-like curves exist, allowing a path through spacetime to loop back to its own past. These solutions remain speculative, but they are fully compatible with the laws of physics as we currently understand them. They suggest that the universe does not forbid time travel outright. It merely imposes conditions so extreme that for now, it remains a theoretical frontier. Even if wormholes were possible, they raise profound questions about causality. Traveling to the past introduces the potential for paradoxes. Could you change events in a way that prevents your own existence? Could actions in the past ripple forward, altering the present? Physicists have debated these questions for decades, proposing mechanisms to preserve consistency. One possibility is that the universe enforces self-consistency, meaning that events in the past cannot be altered in ways that would create contradictions. Another possibility comes from the many worlds interpretation of quantum mechanics, which suggests that changes to the past create alternate timelines, leaving the original timeline intact. In addition to theoretical wormholes, physicists have considered cosmic strings, hypothetical defects in spacetime formed in the early universe, as potential tools for time travel. These strings would be incredibly dense, with mass per unit length so extreme that they warp spacetime around them. Passing near 2 cosmic strings moving at near light speed could, in theory, create closed time-like curves. allowing an object to travel backward in time. Like wormholes, cosmic strings remain hypothetical, but they illustrate the remarkable ways that extreme spacetime geometries could, in principle, enable time travel. At the quantum scale, experiments provide hints that time may be more flexible than our classical intuition suggests. Photons, electrons, and other fundamental particles have been observed in behaviors that challenge our conventional understanding of cause and effect. Experiments with quantum entanglement and delayed choice setups suggest that actions in the present can influence the behavior of particles in ways that seem to retroactively affect their past states. While these effects occur on microscopic scales, they reveal that the universe allows surprising relationships between time and causality. Quantum mechanics also introduces the concept of superposition, where particles exist in multiple states simultaneously. A particle can occupy several locations at once, spin in different directions simultaneously, and exist in multiple energy states until observed. This inherent fluidity of quantum reality undermines the classical notion of a fixed, unchangeable past. It suggests that, at the most fundamental level, the universe is not constrained by linear, one-way causality. If particles themselves can exist across multiple possibilities, it raises profound questions about whether time travel could be consistent with the laws of physics. The interplay between general relativity and quantum mechanics is central to understanding time travel. Relativity governs the large-scale structure of spacetime, describing how massive objects warp space and time. Quantum mechanics governs the microscopic world, where probability and uncertainty dominate. Bridging these two frameworks remains one of the greatest challenges in physics. Theoretical constructs like wormholes and closed time-like curves exist in the overlap of these domains, where extreme gravitational effects meet the probabilistic rules of quantum behavior. Solving this puzzle may one day reveal whether time travel is fundamentally possible, or whether the universe enforces subtle yet absolute prohibitions. As we explore the physics of wormholes and temporal loops, it becomes clear that time is not a passive backdrop. It is a dynamic dimension, influenced by mass, energy, and motion. It can stretch, compress, and even loop under extreme conditions. Understanding these possibilities requires not only mathematics and physics, but imagination, a willingness to envision realities far beyond our everyday experiences. In the next section, we will journey further into the quantum realm, examining time travel paradoxes, quantum experiments that challenge causality, and the potential resolutions offered by modern physics. We will explore how experiments with photons, electrons, and entangled particles hint at a universe where the arrow of time is not absolute, and where backward influence may be subtly encoded in the laws of quantum reality. Time, as it turns out, may be far less rigid than we perceive. It may bend, fold, and intertwine in ways that challenge both imagination and intuition. And in probing these possibilities, we are not merely exploring science fiction. We are venturing into the deepest questions of existence itself, uncovering the hidden architecture of reality that governs every moment of the cosmos. As we journey deeper into the quantum world, we begin to see that time, contrary to everyday experience, may not be an immutable, one-way arrow. On the microscopic scale, particles operate according to principles that challenge classical logic. Quantum experiments have repeatedly shown that events in the present can exhibit correlations with conditions in the past, suggesting that time at its fundamental level is far more fluid than we perceive. One of the most striking examples comes from the delayed choice experiment, first proposed by physicist John Wheeler in the 1970s. In its simplest form, this experiment asks whether a photon behaves like a particle or a wave. Classical intuition would suggest the behavior is determined at the moment the photon passes through a device, such as a beam splitter. Yet in Wheeler's setup, the decision of how to measure the photon is delayed until after it has entered the apparatus. Remarkably, the photon behaves in a way consistent with the measurement choice, as if it knew in advance what kind of measurement would occur. This challenges our classical notions of cause and effect, suggesting that the quantum world does not strictly obey linear time. Entanglement, another cornerstone of quantum mechanics, further complicates the picture. When two particles are entangled, the state of one particle instantaneously correlates with the state of its partner, regardless of distance. Measure one, and you immediately know the state of the other. Experiments have demonstrated entanglement across kilometers, and even in space, with photons transmitted between satellites and ground stations. While entanglement cannot transmit information faster than light in a classical sense, it indicates a deep, non-local connection in the fabric of reality. Some theorists speculate that such correlations could imply hidden temporal connections, where past and future are not strictly separate, but interwoven in ways we are only beginning to understand. Quantum superposition also plays a central role in the discussion of time and causality. In superposition, particles exist in multiple states simultaneously, only collapsing into a definite outcome upon measurement. This means that at the smallest scales, reality is not fixed until observed. Consider Schrödinger's famous thought experiment. A cat in a box exists simultaneously alive and dead until someone opens the box and observes it. While macroscopic objects do not behave this way in everyday life, at the quantum level, the superposition principle is real and measurable. It demonstrates that the past may not be a single fixed reality, but a spectrum of possibilities, each existing until observation solidifies one outcome. These quantum phenomena open the door to profound speculation. If information and states at the quantum level can exhibit correlations that seem to transcend conventional temporal order, could they provide mechanisms, however subtle, for backward influence? Could the probabilistic nature of quantum mechanics allow particles, and perhaps indirectly larger systems, to navigate time in ways that appear paradoxical but remain consistent within the laws of physics? While these questions remain speculative, they inspire experiments that probe the limits of causality and challenge the classical understanding of temporal order. Recent experimental advances provide tantalizing glimpses of such possibilities. In laboratories, researchers have conducted quantum teleportation experiments, where the state of a particle is transmitted to another distant particle, effectively recreating its properties elsewhere. While this process does not allow faster-than-light communication, it demonstrates the ability to transfer information across space instantaneously, hinting at the non-local and non-linear character of quantum reality. Some proposals suggest that similar principles could be applied to time, enabling information or states to influence past configurations within the probabilistic framework of quantum mechanics. Further experiments involve time-entangled photons, where pairs of photons are correlated across different points in time, rather than merely space. In these setups, measurements performed on one photon appear to influence the behavior of its partner, even if the partner has already been detected in the past. These results do not violate known physical laws, yet they reveal that the conventional flow of time is not absolute at the quantum scale. Instead, time behaves as a flexible parameter, entangled with the state of the system and the act of measurement. The implications for time travel, while speculative, are profound. If the quantum world allows retrocausal effects, where present actions influence past outcomes, then the universe may, at its core, be far less deterministic and linear than classical physics suggests. It raises the possibility that closed time-like curves and wormhole-based time travel may not be entirely forbidden, but instead constrained by subtle quantum rules that preserve consistency while allowing non-linear interactions. This is where the many worlds interpretation becomes relevant. According to this theory, every quantum event branches the universe into multiple coexisting realities. If a traveler were to move backward in time, their actions might not alter the original timeline, but instead create or enter a parallel branch. Quantum experiments hint that such branching is not merely theoretical. Superposition and entanglement show that multiple outcomes coexist until observed. In essence, time travel might be possible without paradoxes if reality accommodates multiple histories simultaneously. Another intriguing approach comes from quantum field theory and the concept of negative energy states. In certain configurations, quantum fields can exhibit energy densities that are less than the vacuum, effectively producing negative energy. This is not science fiction. It is a measurable phenomenon in the Casimir effect, where two plates placed nanometers apart experience an attractive force due to vacuum fluctuations. In theory, negative energy could stabilize wormholes or generate conditions for temporal loops, linking quantum mechanics and general relativity in a subtle and extraordinary interplay. The pursuit of experimental evidence continues to push boundaries. Physicists are exploring quantum simulations where complex quantum systems are emulated in laboratory setups. These simulations allow the study of retrocausal effects, temporal correlations, and quantum dynamics in controlled conditions, providing insights into how time might behave under extreme circumstances. Each experiment offers new clues, hinting that time, far from being a fixed and rigid dimension, may be malleable under the right conditions. As we contemplate these findings, it is important to recognize the philosophical and practical implications. The universe, at the quantum level, appears less like a clockwork mechanism and more like a vast web of interrelated possibilities. Time, space, and matter are entwined in intricate patterns, with causality emerging as a statistical rule rather than an absolute law. Understanding these patterns may one day allow us to manipulate time, not in ways that violate physics, but in ways that harness the profound flexibility inherent in the quantum world. In the next section, we will explore theoretical time travel paradoxes and the universe's potential mechanisms for maintaining consistency, including self-correcting timelines and the intriguing hypothesis of quantum branching. We will examine the mathematical and philosophical frameworks that reconcile backward time travel with the laws of physics, and how these ideas could shape our understanding of reality itself. Time, in the quantum universe, is no longer a simple linear progression. It is a dynamic, intertwined tapestry influenced by observation, probability, and the fundamental structure of reality. The microscopic hints we observe may one day illuminate the path to a macroscopic understanding of temporal travel, revealing a cosmos where yesterday, today, and tomorrow are interconnected in ways that challenge imagination itself. As we contemplate the possibility of time travel, we encounter one of the most fascinating and perplexing challenges: temporal paradoxes. These are scenarios in which altering the past could lead to contradictions or impossibilities, highlighting the delicate balance between cause and effect. Among the most famous is the grandfather paradox. Imagine traveling back in time and preventing your grandfather from meeting your grandmother. If successful, you would never have been born to make the journey in the first place. This creates a logical contradiction, a loop with no resolution. The paradox raises a profound question. If time travel is possible, how does the universe prevent such contradictions? Physicists have proposed several theoretical frameworks to address these paradoxes. One approach is the Novikov self-consistency principle, which suggests that any actions taken by a time traveler were always part of history and therefore cannot create contradictions. In this model, you could travel back in time, but events would conspire to prevent any paradox. For example, if you attempted to prevent your grandparents from meeting, circumstances beyond your control might intervene, ensuring that history unfolds as it always did. This principle preserves consistency while allowing the intriguing possibility of interacting with the past. The many worlds interpretation of quantum mechanics offers a complementary resolution. Instead of forcing events to conform to a single, unalterable timeline, it posits that each quantum event spawns a branching universe. If you travel back in time and change an event, you may simply enter or create an alternate branch, leaving your original timeline intact. In this framework, paradoxes are resolved by distributing cause and effect relationships across multiple parallel realities. Time travel becomes less about rewriting history and more about navigating a multiverse of possibilities, where every action has a place without threatening the consistency of any individual timeline. Another layer of complexity emerges when we consider causal loops, scenarios in which events in the future influence events in the past, which in turn produce the future events that influence them. These loops are self-consistent, but challenge our intuitive understanding of causality. For example, suppose you receive a blueprint for a time machine from your future self, construct it, and then send the same blueprint back to your past self. Where did the idea originate? Such loops suggest that information or objects could exist without a clear origin, maintained by the structure of space-time itself. Time travel paradoxes are not mere thought experiments, they are deeply connected to the mathematics of general relativity. Solutions to Einstein's equations that allow closed time-like curves provide frameworks in which these loops can exist without violating the fundamental laws of physics. However, such solutions often involve extreme and unlikely conditions, such as rotating black holes or hypothetical exotic matter. These mathematical possibilities demonstrate that the universe may accommodate time travel in principle, even if practical implementation remains beyond our reach. Quantum mechanics adds further nuance to the discussion. Experiments with entangled particles, delayed choice setups, and superposition reveal that at the microscopic scale, causality can be more flexible than classical intuition suggests. Actions in the present can influence the outcomes of events in the past, at least in terms of correlations, without violating the probabilistic rules of quantum theory. These findings hint that the universe may have mechanisms to maintain consistency even when retrocausal effects occur. Some physicists have proposed that the laws of physics themselves enforce constraints that prevent paradoxes. For instance, certain configurations of spacetime may naturally forbid events that would create contradictions. Wormholes, if they exist, may only permit time travel under conditions that inherently preserve consistency. Similarly, quantum mechanics, with its probabilistic and branching structure, may ensure that every action, even one that seems paradoxical, finds a consistent outcome within the multiverse. The interplay between quantum mechanics and general relativity suggests a universe that is both flexible and self-regulating. Time may be malleable, capable of looping, stretching, and compressing, yet the laws of physics impose subtle constraints to prevent logical contradictions. This delicate balance allows for the theoretical possibility of time travel while preserving the fundamental coherence of reality. Beyond the theoretical, scientists have explored practical thought experiments to understand how time travel might operate. Consider a scenario where a traveler ventures near a rotating black hole, an object so massive and dense that it significantly warps space-time. According to relativity, time near the black hole would slow relative to distant observers. If the traveler were to use a stable wormhole in conjunction with this extreme gravitational field, they might traverse a closed time-like curve, experiencing a form of backward time travel. These scenarios remain speculative, but they illustrate how extreme astrophysical phenomena could intersect with the principles of general relativity to allow temporal loops. The philosophical implications of time travel are equally profound. If backward travel is possible, even in principle, it challenges our understanding of free will, destiny, and the nature of reality. Are events predetermined, constrained by the requirement of self-consistency? Or does each quantum choice branch into multiple realities, granting a form of ultimate freedom within a multiverse of possibilities? These questions intersect with both physics and metaphysics, pushing the boundaries of what it means to exist within time. Experimental hints continue to emerge. In laboratories, physicists study quantum simulations that emulate time loops and retrocausal effects. By manipulating entangled particles and measuring correlations across temporal sequences, they observe behaviors that challenge classical cause and effect logic. While these experiments occur on the microscopic scale, they provide critical insights into how time might behave under extreme or engineered conditions. Each finding adds a piece to the puzzle, suggesting that time travel is not entirely forbidden by the laws of physics, but subject to constraints that preserve coherence and consistency. In contemplating time travel, we are confronted not only with scientific questions, but with profound human curiosity. The possibility of revisiting the past, witnessing historical events, or exploring future outcomes has captivated minds for centuries. While practical time travel remains beyond our reach, the exploration of theoretical possibilities expands our understanding of the universe and our place within it. It reminds us that reality is far richer, stranger, and more intricate than our everyday perceptions suggest. In the next section, we will examine how time travel interacts with cosmology and the large-scale structure of the universe, including rotating black holes. cosmic strings, and the potential role of dark energy. We will explore how the interplay of extreme astrophysical phenomena and quantum principles could, in theory, provide pathways for temporal navigation, bridging the cosmic and the quantum in ways that challenge imagination itself. Time, it seems, is not a fixed river, but a multi-dimensional fabric. Understanding its structure, limitations, and possibilities requires a synthesis of mathematics, quantum theory, and cosmology, a journey that continues to push the boundaries of human knowledge and imagination. To understand the deeper possibilities of time travel, we must look beyond the quantum scale and consider the cosmos itself. The universe, in all its vastness, contains phenomena so extreme that they challenge our intuition and open doors to theoretical time navigation. Among the most remarkable are rotating black holes, cosmic strings, and the enigmatic forces of dark energy. These astrophysical features interact with spacetime in ways that could, in principle, allow movement through time. Rotating black holes, also known as Kerr black holes, differ from the non-rotating Schwarzschild black holes commonly imagined in popular culture. While all black holes warp spacetime with their immense gravity, Kerr black holes also twist the fabric of spacetime around them due to their rotation. This effect, known as frame dragging, causes nearby objects and even light itself to follow spiraling paths around the black hole. In extreme theoretical models, the twisting of spacetime around a Kerr black hole could create closed time-like curves, pathways that loop back on themselves in time. While no practical method exists to enter and survive such an environment, the mathematics demonstrates that space-time under extreme conditions can bend not only space, but time itself. Cosmic strings offer another intriguing possibility. These are hypothetical, one-dimensional defects in space-time, remnants of the universe's earliest moments. Imagine a filament stretching across light years, with density so extreme that it warps space-time around it. Two cosmic strings moving at near light speeds, or a cosmic string and a massive object in close proximity, could theoretically create regions where closed time-like curves exist. In such a scenario, a traveler navigating the right path could, in principle, move backward in time. While no cosmic strings have yet been observed, their theoretical properties illustrate the potential of extreme astrophysical structures to alter temporal experience. Dark energy, the mysterious force driving the accelerated expansion of the universe, may also play a subtle role in our understanding of time. By influencing the rate at which spacetime stretches, dark energy shapes the cosmic environment in which time unfolds. While its direct application to time travel remains speculative, any complete theory of temporal navigation must account for its influence. The universe is not static, it is dynamic, expanding, and evolving, and this evolution shapes the very structure of time itself. In addition to these cosmic structures, theoretical physicists have explored the concept of negative energy densities on cosmological scales. While negative energy has been observed in small-scale quantum phenomena, such as the Casimir effect, scaling these effects to influence macroscopic space-time structures could, in theory, stabilize wormholes or create the conditions necessary for closed time-like curves. The combination of exotic matter, extreme gravity, and the precise manipulation of space-time curvature represents the frontier of theoretical time travel. While the mathematics of these phenomena is elegant, the physical challenges remain immense. Surviving near a rotating black hole, navigating around cosmic strings, or harnessing dark energy are not merely engineering problems. They are fundamental constraints of physics. The immense gravitational forces, radiation, and energy scales involved make practical implementation far beyond current capabilities. Yet the existence of mathematically consistent solutions demonstrates that time travel is not forbidden by the laws of physics. It is constrained by the extreme conditions of the cosmos. These cosmic possibilities intersect with quantum principles in fascinating ways. Quantum mechanics suggests that at the smallest scales, causality is not absolute. Superposition, entanglement, and retrocausal effects imply that the universe allows correlations across time that defy classical intuition. Combining these quantum phenomena with extreme astrophysical environments could, in theory, enable temporal navigation within the bounds of physics. The universe, on both the cosmic and quantum scales, may provide pathways that are currently beyond human reach, but not impossible in principle. Thought experiments further illuminate these possibilities. Consider a traveler entering a wormhole whose mouth orbits near a Kerr black hole. Due to the extreme frame-dragging effect, time near the mouth passes differently than far from it. The traveler could experience a journey in which they return to a past moment, relative to observers elsewhere in the universe. While purely hypothetical, such scenarios are mathematically consistent and demonstrate how extreme cosmological structures could be harnessed for time travel. Another concept of interest is the chronology protection conjecture, proposed by physicist Stephen Hawking. This hypothesis suggests that the universe may inherently prevent large-scale time travel that would create paradoxes. In other words, while the equations of general relativity allow for closed time-like curves, the laws of physics, or quantum effects, might intervene to protect the consistency of causality. This idea highlights a tension between theoretical possibility and physical reality. The universe may permit time travel in principle, but enforce subtle rules that make it effectively impossible on macroscopic scales. Despite these challenges, studying extreme cosmic phenomena provides invaluable insights into the nature of time itself. Rotating black holes, cosmic strings, and dark energy reveal that time is not uniform. It is influenced by mass, motion, and energy in ways that our everyday experiences cannot reveal. Understanding these effects deepens our knowledge of causality, the arrow of time, and the fundamental structure of the universe. Even if time travel remains impractical, these studies illuminate the profound flexibility and complexity of reality. The interplay of cosmic and quantum scales suggests that time is not a simple linear progression. It is a malleable dimension, capable of stretching, bending, and looping under extreme conditions. Theoretical physics provides models in which time travel is possible. Paradoxes are resolved, and causality is preserved. While practical implementation may be centuries or millennia away, the pursuit of understanding expands the boundaries of science and imagination. In the next section, we will explore the philosophical implications of time travel, the multiverse, and how humanity's understanding of time shapes our perception of reality. We will examine not only the scientific challenges, but also the existential questions raised by a universe where the past, present, and future are not rigidly separated. Time, at both the cosmic and quantum level, is a dynamic, intertwined tapestry. By exploring extreme astrophysical environments, the laws of quantum mechanics, and the mathematical structures of spacetime, we begin to glimpse a universe in which yesterday, today, and tomorrow are interconnected in ways that challenge both imagination and intuition. When we gaze into the cosmos and contemplate the nature of time, we begin to realize that the question of time travel is not only scientific, it is deeply philosophical. Every discovery in physics about the structure of time forces us to rethink the very foundations of reality. Are we moving through time, or is time moving through us? Does the universe unfold moment by moment, or do all moments already exist, eternally etched into the fabric of spacetime? These questions are not abstract curiosities. They shape how we understand existence itself. In physics, one of the most profound frameworks for understanding these questions is the block universe theory, also known as eternalism. According to this view, past, present, and future all coexist simultaneously within a four-dimensional structure called spacetime. Just as every location in space exists regardless of where you stand, every point in time exists regardless of when you are. The flow of time, the sensation of moving from moment to moment, may simply be a feature of human consciousness, not a property of the universe itself. In this picture, time travel does not mean moving to a different time that no longer exists. It means traveling to another region of the space-time landscape that was always there. This concept profoundly alters our perception of reality. If the universe is indeed a timeless block, then every event, every joy, every tragedy, every decision, exists forever, woven into the geometry of space-time. The arrow of time, driven by entropy and the increase of disorder, gives us the illusion of progression. But in truth, the universe may be a grand tapestry, where all moments coexist in stillness. Quantum mechanics complicates this picture further. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum event with multiple possible outcomes actually occurs, but in separate, parallel universes. Every decision, every measurement, every interaction branches reality into countless versions, each as real as the next. In this framework, time travel may not alter a single timeline but rather allow one to move between branches of the multiverse. The paradoxes that plague classical time travel vanish, replaced by a landscape of infinite possibilities. Imagine stepping into a machine that allows you to travel to the past, not to change it, but to enter a parallel branch where your actions create a new timeline. In one universe, history remains unchanged. In another, a new reality unfolds. This vision aligns elegantly with quantum mechanics, where the universe continually splits into overlapping probabilities, and every possible history is realized somewhere in the multiverse. This branching reality also redefines the concept of destiny. If every possible outcome exists in some universe, then free will and determinism coexist. Every choice you make defines the version of the universe you experience, while other versions continue in parallel. In this way, time travel, whether through physical mechanisms or through the shifting probabilities of quantum measurement, becomes a journey through the vast architecture of possible realities. Some physicists and philosophers extend this reasoning to suggest that consciousness itself may play a role in selecting or perceiving branches of reality. According to certain interpretations, observation is not merely passive, it defines the outcome of quantum events. If this is true, then awareness may be intimately tied to the unfolding of time. Perhaps the act of observing reality is, in itself, a kind of temporal navigation. We move through time not by physical travel, but through the continuous process of observing, measuring, and collapsing possibilities into the experience we call now. This idea finds echoes in ancient philosophy and modern science alike. From the Buddhist notion of the eternal present to the quantum physicists' description of wave function collapse, there is a shared intuition that the present moment is both fleeting and infinite, the point where potential becomes actual. In this sense, time travel, at least on the level of perception, occurs constantly as consciousness moves from one configuration of reality to the next. The multiverse interpretation also offers a profound resolution to the grandfather paradox and similar logical dilemmas. If every action creates or corresponds to a new universe, then the traveler who prevents their own birth does not erase their origin, but merely transitions to a universe where they never existed. The original universe continues unchanged, while the new one evolves according to the altered circumstances. In this way, paradoxes dissolve, replaced by an elegant multiplicity of timelines. However, the many worlds view also challenges our deepest intuitions about identity. If infinite versions of you exist, each living out different outcomes, what does it mean to be you? Are you the sum of all these versions, or merely one thread in an infinite tapestry? Time travel, when viewed through this lens, becomes not just a physical journey, but an existential one, a confrontation with the vast multiplicity of the self and the infinite branching of destiny. These ideas extend beyond physics into metaphysics, art, and meaning. The possibility of multiple timelines and simultaneous existences forces us to reconsider the nature of purpose. In a deterministic universe, every event unfolds as it must. In a multiverse, every possible event unfolds somewhere. But in either case, meaning arises not from changing fate, but from experiencing it, understanding our place within the immense structure of time and possibility. Philosophers have long debated whether the passage of time is real or illusory. The physicists' equations describe a timeless universe, while human experience insists on the flow of moments. Reconciling these perspectives requires acknowledging that both may be true, each within its domain. From the cosmic viewpoint, all times exist. From the human viewpoint, time flows. Time travel, therefore, sits at the intersection of these truths, a bridge between the static geometry of spacetime and the dynamic experience of existence. Even if technological time travel never becomes possible, exploring these ideas transforms our understanding of what it means to live within time. Every memory, every anticipation, every moment of awareness is an interaction with the dimension of time. We are all time travelers, moving inexorably from the past toward the future at the rate of 1 second per second. But the deeper physics reminds us that this journey may be more intricate than it appears, that the universe may already contain all moments, waiting to be perceived. In the next section, we will explore how quantum information theory, entropy, and the arrow of time intertwine, and how understanding these relationships might bring us closer to a unified theory of time itself. We will examine how information, rather than matter or energy, might hold the key to traversing and comprehending time, and how the laws governing information flow might ultimately define the limits of what time travel can achieve. The exploration of time travel is not only about machines or mathematics. It is a reflection of our deepest desire to understand reality. Whether through quantum branching, cosmic structures, or the timeless geometry of the universe, time travel symbolizes humanity's quest to transcend limitation, to see beyond the horizon of now, and to glimpse the eternal fabric of existence. At the heart of the mystery of time travel lies a deeper question: what is time itself? Is it a river that flows from the past to the future? Or is it something even more fundamental, a property of information, an emergent phenomenon arising from the quantum fabric of the universe? To explore this, we must venture into one of the most fascinating intersections of physics, the relationship between entropy, information, and the arrow of time. In the everyday world, time appears to have a clear direction. We remember the past, but not the future. Eggs crack but never uncrack. Stars burn fuel, radiate light, and fade into darkness. This asymmetry, this one-way flow of events, is known as the arrow of time, and it is intimately connected to the second law of thermodynamics. Entropy tends to increase. Entropy is often described as disorder, but more precisely, it measures the number of possible microscopic configurations that correspond to a macroscopic state. The more ways a system can be arranged, the higher its entropy. From this principle, time's direction emerges. The universe began in a state of extraordinarily low entropy, a condition of remarkable order. As it expands and evolves, entropy increases, driving the apparent flow of time from past to future. In this sense, the arrow of time is not an inherent feature of the laws of physics, but a statistical property of how those laws manifest on large scales. At the microscopic level, the fundamental equations of physics, whether classical, relativistic, or quantum, are time-symmetric. They work equally well forward or backward in time. The asymmetry we experience arises not from the equations themselves, but from the initial conditions of the universe. This realization opens a profound possibility. If time's arrow emerges from entropy, could manipulating entropy allow us to manipulate time? On a microscopic scale, quantum mechanics shows that processes can run in both directions. Quantum entanglement, for example, creates correlations that transcend time. When two particles are entangled, measuring one instantly determines the state of the other, regardless of distance or even temporal separation. In experiments such as delayed choice quantum erasers, decisions made in the present appear to influence the outcomes of measurements made in the past. While this does not allow classical time travel, it suggests that information may not be bound by the same temporal limitations as matter and energy. Information, in many ways, is the true currency of the universe. The equations of quantum mechanics describe not objects but information about possible states. The universe itself may be best understood as a vast information processing system, where physical laws govern the transformation and transmission of information. In this view, time emerges not as an independent dimension, but as a measure of how information changes. The past is the record of information already processed. The future is information yet to be determined. Physicist John Archibald Wheeler famously summarized this idea with 3 words: it from bit. According to Wheeler, every particle, every field, every event derives its physical existence from binary choices, yes or no, 1 or 0, encoded in the quantum fabric of reality. Time, then, may be the unfolding of these informational transitions. If information can be reversed, in theory, time could be reversed. This perspective aligns with recent advances in quantum information theory. Quantum computers, for example, exploit the superposition of states to perform calculations that, in some sense, explore many possible timelines simultaneously. When a quantum computer processes data, it doesn't simply move forward in time, it evolves across a landscape of probabilities, collapsing into a final outcome only when observed. Some theoretical models suggest that quantum computation itself could simulate time reversal, allowing researchers to rewind quantum systems under controlled conditions. In 2019, a team of physicists used a quantum computer to perform a small-scale time reversal experiment. They programmed the system to evolve forward in time, then used quantum algorithms to reverse that evolution, effectively restoring the system to its earlier state. While this was not time travel in the classical sense, no one traveled through time, it demonstrated that time's arrow is not absolute. Under the right conditions, quantum information can flow backward, at least locally and temporarily. This revelation bridges the microscopic and macroscopic realms. On the quantum scale, time appears reversible. On the human scale, it flows inexorably forward. The transition between these regimes may hold the key to understanding how time travel could occur without violating physical laws. If time is the product of information flow, then time travel might involve manipulating how information is stored, transferred, and perceived within the universe's quantum framework. This brings us to the concept of quantum entropic control, the idea that by altering the entropy or information structure of a system, one could theoretically navigate temporal dimensions. For example, stabilizing a wormhole might require not only exotic matter with negative energy density, but also a precise manipulation of quantum information to maintain consistency across time. The relationship between entropy, information, and gravity, hinted at by the holographic principle, suggests that the surface area of a region of space encodes the information within it. Time, therefore, may be an emergent feature of this informational geometry. If the universe is holographic, every moment of time could be encoded on the boundaries of spacetime, much like frames of a film encoded on the surface of a cosmic screen. Time travel, in this sense, might not mean moving through time as a physical dimension, but accessing different frames of this cosmic information landscape. Advanced civilizations, or future humans, might learn to decode and re-enter these stored states of information effectively, reconstructing the past or projecting into potential futures. However, the manipulation of time through information comes with deep philosophical and physical implications. Information, according to the law of conservation of information, cannot be destroyed. Even when matter falls into a black hole, the information it carries is not lost, it is encoded on the event horizon. This realization, known as the black hole information paradox, led to groundbreaking insights into the nature of time and reality. If information is truly eternal, then every moment that has ever existed continues to exist in some form, embedded in the informational structure of the cosmos. Time travel, then, may be less about moving through time and more about accessing information that never truly vanished. This understanding transforms the idea of the past from something gone into something hidden. The past may be encrypted in the quantum state of the universe, retrievable in principle if one can decode the vast complexity of that information. Likewise, the future might already be implicit within the current state of all quantum interactions, waiting to unfold through the continuous evolution of information. When viewed through the lens of information theory, the boundary between time and memory blurs. Memory itself is a form of time travel, a reconstruction of information that allows the mind to revisit past states. Dreams, imagination, and prediction are similarly forms of mental time travel, exploring informational possibilities within the brain's quantum-like processing. If consciousness is indeed an emergent property of quantum information, then perhaps every act of remembering or imagining is a microcosmic reflection of the universe's own temporal dynamics. In the grand tapestry of physics, entropy and information form the threads from which time is woven. The flow of information defines the direction of time. The accumulation of entropy defines its passage. If humanity ever learns to reverse or manipulate these flows, we may find that time travel is not a violation of nature, but an extension of it, a deeper understanding of the rules that govern the cosmic game. In the next section, we will explore how time travel, if achieved, could reshape civilization, technology, and our understanding of existence itself. We will move from theory to imagination, contemplating the profound consequences of mastering time, not only its scientific potential, but its moral, existential, and cosmic implications. Time, seen through the prism of entropy and information, is no longer a linear march. It is a vast, interconnected network of possibilities. The key to unlocking its secrets may not lie in machines that move us through time, but in understanding the informational code that creates the illusion of time in the first place. If time travel were ever achieved, not as a dream, not as a theory, but as a reality, the consequences would reverberate through every aspect of civilization. From the structure of society to the nature of morality, from our understanding of history to the meaning of the future, everything we know about existence would be reshaped. Time travel would not simply be another scientific milestone, it would be the most profound transformation in human history. To begin with, time travel would alter our relationship with knowledge itself. Imagine a civilization that can observe any moment in history directly, not through archaeology or memory, but through temporal exploration. Ancient mysteries, from the birth of galaxies to the origins of life on Earth, could be witnessed firsthand. The truth of every event, every secret, every story would be accessible. Human history, which has always been a tapestry of partial truths and interpretations, would become an open book. Such power could usher in an age of unprecedented enlightenment or an era of profound instability. The ability to travel through time would also challenge our understanding of free will and responsibility. If the future can be observed, can it be changed? If the past can be revisited, can it be rewritten? In the classical view, causality flows forward. Actions produce consequences, and those consequences shape the next actions. But in a world where time is malleable, cause and effect could intertwine in unpredictable ways. A single intervention in the past might ripple outward, altering the entire course of civilization, or perhaps merely branching reality into a new timeline, leaving the original intact. Such questions would demand new ethical frameworks. Should we, for example, intervene to prevent tragedies if given the chance? Would changing history erase lives that would otherwise have existed? The morality of time travel would be far from simple. It would require a deep understanding of causality, consequence, and the delicate balance of existence. Time travelers might become custodians of temporal integrity, bound by strict codes to avoid paradoxes or catastrophic alterations. Perhaps a form of chronological ethics would emerge, a new branch of philosophy dedicated to the moral use of temporal power. The technological and political implications would be equally staggering. Nations and corporations would compete for control over time travel technology, viewing it as the ultimate strategic advantage. The ability to foresee or influence future events could reshape global power structures overnight. Wars could be prevented or rewritten. Economies could be manipulated with perfect foresight. Scientific breakthroughs could be imported from the future, collapsing centuries of progress into moments. The line between innovation and exploitation would blur. Yet, as history has shown, with great power comes profound risk. Time travel technology could easily become the most dangerous weapon ever conceived. Even minor alterations to the past could produce unintended consequences. A single individual, acting with ignorance or malice, could reshape the fabric of reality itself. The temptation to correct perceived injustices or rewrite unfavorable outcomes would be immense. Preventing misuse would require not only technical safeguards, but an evolution in human wisdom and restraint. Cultural and psychological effects would also be profound. Humanity's perception of mortality and destiny would change forever. If the future could be visited, the mystery of death itself might be confronted. Would people still fear the unknown if they could glimpse what lies beyond their time? Would art, religion, and philosophy lose their meaning, or would they evolve into deeper explorations of timelessness? Time travel could dissolve the boundaries between generations. The living and the long dead could coexist in dialogue, sharing wisdom across centuries. History would no longer be a record of what once was, but a living continuum. From a scientific standpoint, the discovery of practical time travel would revolutionize physics. It would provide direct evidence for the unification of general relativity and quantum mechanics, the long-sought theory of everything. Mastering time would mean mastering space-time geometry, energy manipulation, and quantum coherence on a scale previously unimaginable. Technologies based on such mastery could include instantaneous communication across light years, interstellar travel through space-time shortcuts, and even control over the rate of biological aging. Humanity would no longer be bound to the linear progression of time. Existence itself would become multidimensional. But even in this vision of near omnipotence, limits would remain. The chronology protection conjecture, proposed by Stephen Hawking, suggests that quantum effects may always act to prevent paradoxical time loops on macroscopic scales. In this sense, time travel might remain possible only in constrained or simulated forms. Perhaps humanity would learn to create virtual timelines, computational universes in which time can be explored safely without altering the real one. Within such simulations, travelers could experience the full scope of temporal exploration, past, future, and alternate histories, without endangering causality. This raises yet another philosophical question. How would we know if our own universe is not already such a construct? If advanced civilizations have learned to manipulate or simulate time, perhaps what we experience as reality is itself a temporal simulation, an informational structure designed to explore the infinite possibilities of existence. The notion may seem speculative, but it aligns with the growing realization in physics that the universe behaves like a computational system, governed by the flow and transformation of information. In the human realm, time travel would also redefine memory, history, and identity. If we could revisit our own past experiences, would our memories remain stable, or would revisiting them alter who we are? The continuity of self, the narrative that each individual constructs over a lifetime, depends on the linear progression of time. Break that progression, and identity itself might fragment. The self could become multi-dimensional, existing in many forms across many timelines. To travel through time might be to meet not only one's ancestors, but one's alternate selves, reflections of what could have been or what might yet be. Artists, philosophers, and poets would find new meaning in a universe where time is fluid. The creative imagination, long fascinated by the idea of revisiting the past and glimpsing the future, would find reality catching up with its dreams. Perhaps new forms of storytelling would emerge, chronotemporal art that unfolds across different moments simultaneously, allowing audiences to experience multiple timelines as one. Human creativity, liberated from the boundaries of linear time, could express the multidimensional nature of existence in ways we can scarcely imagine today. At the same time, the emotional dimension of time travel would be inescapably human. Imagine the possibility of seeing lost loved ones again, of revisiting moments of joy or regret. The temptation to return to the past, to relive or change what once was, would be powerful. But each journey backward would raise new questions. Are we meant to alter the past or to learn from it? Does revisiting history diminish its meaning or deepen our understanding of it? Perhaps the greatest wisdom in time travel would lie not in changing time, but in understanding its true nature. Ultimately, the realization that time is flexible, reversible, and interconnected would force humanity to redefine its place in the cosmos. We would see that we are not isolated beings moving helplessly through a one-way stream, but participants in a vast temporal web, co-creators of reality itself. Time travel, if achieved, would not simply make us masters of time, it would make us students of existence, learning that every moment, past, present, or future, is part of a single unified whole. In the next and final section, we will bring these threads together, exploring what time travel ultimately teaches us about reality, consciousness, and the destiny of intelligence in the universe. We will look beyond the mechanics of time travel and ask the ultimate question: what is the universe telling us about itself through the very possibility of time travel? Because in the end, time travel is not just about moving backward or forward. It is about understanding that all of time, every heartbeat, every thought, every star, is part of an eternal, interconnected dance. To master time is to understand that the past and future are not distant. They are alive within us, in every moment of awareness, in every spark of existence that connects us to the infinite. Throughout our journey into the mysteries of time travel, we have traversed the landscapes of quantum physics, general relativity, cosmology, and philosophy. We have seen how time, once thought to be a simple and constant flow, is in fact a dynamic, malleable dimension, woven into the very structure of reality. We have glimpsed the strange possibilities that arise when physics bends to its extremes, where particles can influence the past, where gravity warps the flow of time, and where the universe itself might contain infinite versions of every moment. But as we reach the end of this exploration, one question remains: what does all of this reveal about us and about the universe itself? To understand time is to confront the deepest mystery of existence. Every living thing is bound to it, shaped by it, and ultimately returned to it. Yet physics shows us that time is not fundamental, it is emergent, arising from the deeper relationships between energy, matter, and information. If the laws of nature are timeless, then perhaps what we experience as the passage of time is simply the unfolding of patterns, the evolution of states within a cosmic computation. The universe may not move through time, it may simply be a timeless whole within which all events coexist. In this view, the past, present, and future are not sequential, they are simultaneous, woven together in the vast geometry of spacetime. We, as conscious beings, experience this geometry one moment at a time, like reading a story word by word. But the story itself, the entire narrative of the cosmos, already exists. From the birth of the universe to its distant future, from the first atoms to the last stars, every chapter is part of a single cosmic book. Time travel, then, is not about jumping between moments that appear and vanish. It is about exploring the pages of a book that has always been complete. Quantum physics hints that this timelessness is not an abstraction but a fundamental truth. At the quantum level, events do not occur in a strict sequence. Cause and effect blur, probabilities intertwine. In some interpretations, time emerges only when the quantum world is observed, when consciousness interacts with possibility and turns it into experience. If so, then time and awareness may be two sides of the same coin. To travel through time might mean more than moving through the universe. It might mean changing the state of consciousness itself, shifting the point of observation within the infinite field of potential reality. This realization brings us to a profound convergence between science and philosophy. From the ancient mystics who spoke of eternal now, to the modern physicists who describe spacetime as a static four-dimensional manifold, the message seems the same. Time does not pass. We do. We are the travelers, moving through the vast landscape of existence, perceiving one slice of reality at a time. The river of time flows not through the universe, but through the mind. If consciousness plays a role in the unfolding of time, then the future of time travel may lie not only in machines, but in understanding the mind itself. Perhaps the ultimate time machine is not a physical device, but the power of awareness, the ability to perceive reality beyond the limitations of linear experience. Some theories of physics already suggest that consciousness and quantum information are intertwined. If that connection is ever understood, it may allow us to navigate not just through space, but through the very structure of time and existence. And yet, even as we contemplate these vast possibilities, time remains deeply human. It defines our lives, our memories, our hopes. We mark its passage with rituals, measure it with clocks, and feel its weight in every heartbeat. The dream of time travel, at its core, is a reflection of our longing to revisit moments we have lost, to glimpse what lies ahead, to transcend the impermanence that defines us. It is not only a scientific pursuit, but a profoundly emotional one. In every human heart lives the wish to rewrite the past, to correct mistakes, to relive joy, to hold on to what fades. And in every mind lives the curiosity to see the future, to understand what we are becoming. These desires are not separate from science, they are what drive it. The quest to master time is the ultimate expression of the human spirit, the refusal to accept limitation, the unending pursuit of knowledge, and the deep intuition that we are part of something eternal. If one day humanity learns to travel through time, it will not be an escape from destiny, but a deeper engagement with it. We will come to see that time is not an enemy to be conquered, but a teacher. It reminds us that change is the essence of existence, that creation and decay, birth and death, past and future, are all expressions of the same cosmic rhythm. Time gives meaning to existence. Without it, there would be no story, no growth, no evolution. Even if we master it, we will still need it, to experience, to learn, to become. As we look to the future, the boundaries between science and philosophy may continue to blur. Quantum mechanics and cosmology are already leading us toward a picture of reality, where the observer and the observed, the mind and the cosmos, are inseparable. Time travel, if ever achieved, will be more than a technological triumph. It will be a revelation about the unity of all things. It will show us that the universe is not a machine made of separate parts, but an organism, alive with connection and coherence across time and space. Perhaps, in the deepest sense, we are already time travelers. Every thought, every memory, every dream is a journey through time. When we remember, we travel to the past. When we imagine, we travel to the future. When we love, we transcend both. The flow of time may be an illusion, but the experience of it is what makes us human. In the end, whether or not physical time travel becomes possible, the exploration of time itself changes us. It expands our understanding of reality and deepens our sense of wonder. It teaches us that the universe is not static, not cold, but filled with motion, potential, and mystery. It reminds us that everything, every atom, every star, every being, is part of an endless story, written in the language of time. So perhaps the question is not can we travel through time, but how do we already do it? Every moment we live, every choice we make, sends ripples through the future. Every act of kindness, every discovery, every dream alters the shape of what is to come. We are shaping time constantly through our actions and awareness. The universe may be timeless, but within that timelessness, we create meaning. As the universe expands and stars burn and fade, as galaxies drift through the cosmic sea, time will continue to weave its endless pattern. One day, perhaps far beyond our current understanding, humanity may step beyond the boundaries of temporal experience and see the universe for what it truly is, a single eternal whole, shimmering with infinite moments. And in that moment of realization, we may understand that time travel was never about reaching backward or forward. It was about awakening to the truth that all of time, every past and future, already exists within the vast consciousness of the cosmos. To know time is to know the universe. To know the universe is to know ourselves. Because in the end, time is not something we move through. Time is something that moves through us.